Good afternoon all. Welcome back to the last and very special lecture by Professor Altman. Because I can see there are many members who are now came just for this lecture, and so I just wanted to tell you a brief about Professor Altman and also about the GAN course. Professor Altman is a full professor and holds Stephen Lee and Taglian Chair in Pharmacy with appointments in Bosch Department of Medicinal Chemistry and Molecular Pharmacology, and James Tarpo Jr. and Margaret Tarpo, Department of Chemistry. Dr. Altman received BS Chemistry from Creighton University in 2003 and PhD in Organic Chemistry from MIT 2008. Studying as a Pfizer and National Institute of Health postdoctoral fellow in Professor Buchwald's laboratory. He subsequently trained as an NIH postdoctoral fellow at Professor Larry Overman at UC Irvine, and then joined Department of Medicinal Chemistry at the University of Kansas as an assistant professor in 2011. During this time, I was a postdoc over there, so I got to know Professor Altman. And because of that association, we wrote like a GAN course. It was actually a teaching course which he has already delivered last 5 days. It was just completed before lunch. And because I just wanted to benefit many of the student research scholars who could not attend this course, so I requested him to give a lecture on his research, what is going on. And he has very kindly agreed. This is a very special lecture because it's a 2-hour lecture. So we will be taking maybe a 5 minutes break in between. Okay. So after working at KU for up to 2017, he moved to Purdue University. In 2017 at KU he got associate professor. And then he moved to Purdue University as a full professor in 2020. The Altman's group works at the interface of synthetic organic and medicinal chemistries with synthetic emphasis in the area of organometallic and organofluorine transformations, and with collaborative medicinal interest spanning a range of diseases including pain, anxiety, mood disorders, aging, and immuno-oncology. Professor Altman has taught a variety of topics at the undergraduate, graduate, and professional levels, including organic chemistry, medicinal chemistry, biochemistry, and a broad range of therapeutics area. Dr. Altman is a chair of the National Institute of Health, Chemical Sciences, and Biosynthesis Study Section. So, Professor Altman, we really enjoyed the kind of teaching course he has delivered, and we are really looking forward to your this special lecture for all the students. So, with this, I invite Professor Altman to deliver this talk.
So hello again, everybody. Welcome back to those of you who have been here all week. Welcome to some of the new individuals here who are here for the first time. I'm happy to continue to share science in this last little stint. It is a 2-hour lecture, as mentioned, and I've actually never given a 2-hour lecture, so the estimate of time is going to be, maybe a little bit off. We'll find a nice time to break, just to get a couple of minutes for everybody to reset, stretch, get a quick trip to the washroom, water, whatever you need. So this is the fun lecture. This is where we get to talk about the passion of the research. Everything else I've shown, most of what I've shown you before is other people's works. I've snuck in a couple of the small stories from my group in the medchem realm. In this case, I've chosen to teach more about the synthetic chemistry and to think about chemical reactivity. And we might be able to relate some of the concepts here to the fundamental concepts we would have discussed in day 1. The perturbation of reactivity. So, I probably don't need to do a full introduction of my research group and my interests. We are organic chemists by training, organometallic chemists, natural product total synthesis chemists by training, but in initiating my career, I was really intrigued in fluorine chemistry, and so we predominantly focus most of our synthetic chemistry, medicinal chemistry, around this element. And it's a really interesting element for many reasons that I've described before. Maybe one other interesting fun fact, it's the only element that has a journal dedicated to it. So you have the Journal of Fluorine Chemistry. Other than maybe the Journal of Organic Chemistry, organic chemistry is carbon chemistry, so maybe there's an argument there, but other elements don't get their own journal just for one element. So this has been a fun area. In terms of medicinal agents, you've seen over the course of the week that the physicochemical perturbations imparted by fluorine and fluorinated substructures influence the interactions between the chemical matter and the biological system. They perturb drug-like properties, and as a result, it's essential to prepare fluorinated molecules. You want to prepare them well, you want to prepare them efficiency, high yield, high selectivity. And so you need efficient strategies to be able to introduce fluorine exactly where you want in a molecule. There's a fundamental challenge, though. It's really tough to install fluorine in a controlled manner into your molecules. So classically, most of the reagents that are used are harsh, gaseous. They're toxic agents, things you don't want to breathe. You don't want to be in the same room. You can't do many of the classic reactions in an academic laboratory. You need to do it in an industrial setting. I'll show you some examples as we move forward. Fluorinated molecules also have distinct reactivities, so the electronegativity, the hyperconjugative effects. In many cases, those effects disfavor reactions that would normally work on non-fluorinated compounds, and when the reaction doesn't work, you need specialized solutions, specialized reagents, specialized catalyst systems, distinct reactivity patterns, distinct mechanisms to promote reactions that are going to be different than the standard organic chemistry that you learn, okay? In your coursework. Okay, so there are new rules, there are different sets of reagents, different specialized reactions. There are also innovative activations of alkenes or other functional groups that occur through fluorination, and so you get unique innovative reactivities that you can exploit, and hopefully those themes are evident in today's talk. So I'll go back to, I'll start the story back when I was a grad student. And when I was a grad student, I had an interest in organofluorine chemistry just as an intellectual inquiry. Okay, and so this was just a question in my head, like why do drug-like properties get perturbed the way they do? And that curiosity led to the writing of a proposal in grad school about how to prepare fluorinated compounds. And the starting point for that proposal was this thought right here. If you took a hydroxyl group, we can convert that hydroxyl group into a fluorinated compound. It's a deoxyfluorination reaction. At this point, there are dozens of reagents that will do this transformation. So I won't say it's a totally solved problem, but there are many solutions. Who knows which one might work for any given organic molecule? But if we take this deoxyfunctionalization concept and instead extrapolate it to other important fluorinated substructures, how would you accomplish this transformation? So this could be useful for a variety of applied chemists because you're taking these oxygen atoms that can serve as good proton donor or accepting groups, and you can do a lot of further transformation with the alcohols. Okay, they're feedstock chemicals. You find them in libraries. We know how to synthesize them. It's a great substrate to use for any transformation, these types of substrates. If we could convert those into fluoroalkyl groups in efficient, direct strategies, we would drastically perturb the properties of the molecules. And again, perhaps that's useful for a variety of applied industries. That was the general thought, and I wasn't sure how to do that, and I'll show you some of the solutions to that and how we've improved some of these processes over time. The group has generally explored deoxygenative strategies, decarboxylative strategies, or a subset of deoxygenative strategies, and then reactions of fluorinated alkenes. For purposes of today, I'm just going to talk about that first strategy. We're going to ignore quite a bit of work that we've done in the reactions of fluorinated alkenes. Now, the initial inquiry, the initial train of thought started with deoxy-trifluoromethylation reactions, but I'm also going to demonstrate that with these strategies, we can make more and more and more fluoroalkyl groups that are important for my biomedical processes, and we've seen some of these over the course of the day. Some of these guys perturb basicity, benzylic positions, blocked. Okay, we talked about some of these substructures already and why they're relevant, so at this point, I'm going to not try to rationalize all the different substitutions that we're interested in, and this is just a subset. Okay. So the roadmap for the talk is here. In a 50-minute talk, I wouldn't maybe cover all of these, but in the case we have a little bit more time, I'm going to cover several different strategies that involve this deoxyfluoroalkylation strategy, a subset of strategies. There are several different catalyst systems here. You can see copper, palladium, you can see no catalyst system on the bottom. So we've taken this reaction pretty far, and hopefully I can tell a good story here. And I will tell a bit of the background in some of these reactions since I have a little bit of time, a little bit more of the thinking behind the scenes that went through, a little bit more of the problem solving. Some of that might be appreciated by the students. So I'll start back. This is Assistant Professor Day. Dr. Deepak was a postdoc at Kansas, and my group started doing that right there when he was a postdoc on about a mile away on a different side of campus. So in the literature, there is a solution to this deoxy-trifluoromethylation reaction. It requires a 4-step synthesis. In that 4-step synthesis, you first oxidize the alcohol to a ketone or aldehyde, use the Rupert-Prakash reagent to promote a 1,2 addition reaction and make a trifluoroethyl alcohol. This reagent, when combined with fluoride, will basically make CF3-, which can do 1,2 addition reactions. And that's how you get the alcohol. So it's just a 1,2 addition reaction of CF3- to a carbonyl. Subsequently, deoxygenation of the hydroxyl group is required, and there are multiple different ways you can do this. Functionalize the alcohol and do some type of reductive step. Okay, so there are multiple solutions for steps 3 and 4. Not necessarily a green process. Process chemists would hate this one, right? Workup, purification on every single step. Not necessarily green solvents in many cases. And you also have unnecessary redox steps. So we're taking an alcohol and oxidizing it just so that we can reduce it off later. Okay, it's a waste of steps if you can figure out how to more directly connect the oxygen to the trifluoromethane. Nonetheless, this strategy has been used to make quite a variety of biologically active molecules, fragments for drugs, biological probes in themselves. You can see nucleosides, amino acid derivatives, other small synthetic molecules that contain heterocycles, sugar mimetics. Like this type of strategy works in many cases. But certainly not green, not ideal, and the goal from the outset was to figure out a 1-step strategy to go from the alcohol or the ketone and get to the trifluoromethane. Very process type thinking, like process chem type thinking, but the inspiration comes from medicinal agents, and how could we improve the access to medicinal agents. So the initial strategy explored involves a decarboxylative reaction in which a halodifluoroacetate derivative decarboxylates in the presence of a copper-based salt and a metal fluoride under thermal conditions. The release of CO2 is an exothermic process. The process generates a metal halide salt. So if we start with the bromide of the chloride, that would generate a metal bromide or chloride salt as a stoichiometric byproduct that crashes out of the system. The copper CF3 is intrinsically nucleophilic and can do coupling chemistry with some type of electrophile. For purposes of the first part of the talk, we're talking about activated CSP2X electrophiles. Okay. Sorry, CSP3X electrophiles. Okay. So these are generally going to be benzyl, allyl, propargyl type substructures here. These are mild conditions. You'll see for the decarboxylation, we minimize waste by doing this in 1 or 2 steps, and ultimately these are inexpensive reagents when you go look them up in any chemical catalog. The foundations for the reactivity I'm exploring come from Professor Chen's group at the Shanghai Institute of Organic Chemistry, who in a series of manuscripts nearly 30 years ago, over 30 years ago now, had reported this sequence in which the alcohol can get converted to the halodifluoroacetate ester. Isolate, purify, subject that to stoichiometric quantities of copper in addition to sometimes catalytic cadmium, which is a toxic additive. So it was a stoichiometric process that would occur, and we evaluated the mechanism by which he proposed this reaction occurs. I don't want to walk line by line through everything. I would like to highlight maybe 3 key points about that mechanism that really inspired a lot of the thinking behind the scenes. So initially, the reaction started with copper iodide. The final step generated more copper iodide. So in principle, a catalytic process should be feasible in which we can reuse the copper. Pretty simple principles of catalysis here. In his reaction, the initial step of the reaction would generate, see the reaction of copper iodide plus your substrate generates an alkyl, benzyl, allyl iodide. And that would ultimately serve as the electrophile that undergoes trifluoromethylation at the end. So perhaps we need to modulate the concentration of iodide if we want to facilitate formation of this species. It turns out that that working hypothesis works in some cases, not others, on a substrate by substrate basis, and I'll explain that in a little bit. But again, it's something that was in the back of our minds certainly throughout the process. Finally, in Dr. Chen's reports, they estimated that the reaction would generate free difluorocarbene. That difluorocarbene could react with a metal fluoride salt, generate CF3-, which would ultimately give us the copper CF3. Now, in this process, the free difluorocarbene formed in the reaction could decompose many useful functional groups and molecules. And so if this mechanism is true, there's necessarily limitations in functional group compatibility. It'd be difficult to have alkenes, it'd be difficult to have acidic NH bonds and things like that. So if this is true, there are quite a few things that you cannot do with this difluorocarbene. I'll argue for a different mechanism. I'm going to argue for an inner sphere decarboxylation for which there's no free difluorocarbene floating around in solution, and I'll show you that in just a little bit. So this is assistant professorhood. This is year one. Brett Ambler started this project, and ultimately other individuals continued over time. And further developed this project. But Brett really started this. He was one of my first graduate students. And over the series of a couple of years, he led a series of studies that did indeed accomplish catalytic processes. So in this case, we take the alcohols, the allylic alcohols, preform the halodifluoroacetate esters, and using copper-based catalyst systems, in this case using DMEDA, a ligand popularized by my PhD mentor, promoted the decarboxylative trifluoromethylation reaction. The benzylic substrates could also be converted. In this case, we don't use nitrogen-based ligand. And in this case, we do add extra Ki. And so that's what I was saying. Some of these substrates benefit from the addition of more and more and more Ki. And that certainly was true for the benzylic substrate. And finally, the propargyl substrates could react with distinct ligands, DMEDA or 1,10-phenanthroline, to generate either propargyl or allynyl products in a ligand-dependent fashion. And the ability to control the regioselectivity of the transformations by the ligands was a key feature of this chemistry. So that's older chemistry. It's published. The combined series of reactions that occur under reasonably similar conditions tolerate a wide variety of functional groups. You can have O, N, S in your substructures. You can have halides and pseudo-halides built into your substructures. A variety of heterocycles are tolerated, nitro groups, alkene groups that can undergo further functionalization. Importantly, the reaction actually tolerates a variety of ketones and esters and aldehydes and acidic NH protons. And the compatibility of those substrates suggests that, number one, you don't have free CF3- in the reaction. The decarboxylation and the formation of the copper CF3 must occur within the solvent sphere of the metal. Otherwise, these functional groups would react with CF3- and additionally with difluorocarbene. So maybe I'll go back one more step. Difluorocarbene can react with acidic NH bonds. It can react with alkenes. So it's arguing for a distinct mechanism for decarboxylation and formation of the copper CF3 species. There were still some limitations, some things that don't work, basic alkylamines, pyridines, quinolines. That was something that we've been working on for some time, and we partially solved that. Now, if you're looking at the value of these products for medicinal chemistry, an analysis some years ago indicated there were tens of thousands of compounds reported in patents that would have these trifluoroethyl substructures that you see here. So others in the field, in the medicinal chemistry field, were trying to make these for various reasons. So it seems like a reasonable target to try to improve, to which we can improve the access. Additionally, the trifluoromethyl allyl substructures can be further functionalized by either oxidation chemistry or reduction chemistry to make simple fragments that could be elaborated into more complex biomedically relevant substructures. Okay. So these are reasonable enough fragments. Again, we can improve the preparation of those. Somebody else can use them in their medicinal chemistry campaigns. We are happy with that. The allynyl products that would be formed from the propargyl substrates could be further functionalized to generate a variety of carbon-nitrogen, carbon-carbon, carbon-oxygen, and carbon-boron bonds with exclusive regiochemistry. So these are chemoselective processes. You have two alkenes There's 3 different positions here that you could maybe form that carbon-boron bond, right? You could form it here or there or there. In every case, we exclusively get formation of whatever bond we form. We get it exclusively at one position. Now, there are different mechanisms for these, so we can't like walk through every single example here, but this was an attempt to demonstrate that you could access nice fragments from this type of a trifluoromethylalene substructure. Mechanistically, this reaction occurs by a process that we propose looks something like this. At the start of the reaction, we have a copper halide ligated by some type of nitrogen-based ligand in 2 of those 3 systems. There's an initial activation step in which the copper iodide reacts with the halodifluoroacetate and KF before the catalytic cycle initiates to generate the copper CF3. So when we run these reactions, many times we mix this combination together first, about 10 minutes, 15 minutes, a little bit of heat, maybe 50 degrees, maybe 80 degrees, based on which system we're dealing with. That generates the copper CF3, then you put in the substrate and start the reaction. Okay? So we do that sometimes. We do it for the allyl system, we do it for the propargyl system. It doesn't benefit the benzyl position. From there, our copper CF3 is the nucleophilic species that can react with an electrophile, and there are various different electrophiles that seem to vary according to the structure of the R group. So in the case of the allylic electrophile, we can actually run the reaction in the absence of iodide. So we can start with a copper PF6 or copper BF4, no iodide at all, and those reactions perform just fine. So we think that's a system for which we don't go through an iodide intermediate. In contrast, for the benzyl electrophiles, we add excess iodide, and we can track by GC the buildup of iodide over the course of the reaction. The highest concentration of iodide simultaneously occurs at the maximum rate of the reaction, and then as that concentration falls off, you also see the overall rate of the reaction similarly fall off. So evidence that benzyl iodide is a key intermediate. So in the benzyl case, we think it's the iodide. In the propargyl case, we speculate that the electrophile, which is initially that bromodifluoroacetate, converts to a bromide, and we've done stoichiometric studies pushing material forward one step at a time, one step at a time, one step at a time to demonstrate that progress. Okay. So the propargyl likely go through the bromide. Now, after the substitution process, we ultimately get back to a copper difluorobromocarboxylate species, and this does an intersphere decarboxylation. It generates a copper carbene species. That copper carbene is intrinsically electrophilic at this position, so fluoride can add into this position and get you back to your initial copper CF3. Okay, so it's an electrophilic carbene at C for this case. You have Fischer carbenes and Schrock carbenes. This is a Fischer carbene. So that's the intersphere decarboxylation. This is how we rationalize not having free CF3 minus or difluorocarbene floating around in solution. So that's great, that's wonderful. That is a series of publications to get your career started. That we didn't hit our goal. The initial goal was to get a one-step process. And this required 2 steps, so we have some inefficiency in atom economy and step economy there. You have to isolate, purify this material, run a column. Some of them are a little bit unstable, and so certain functional groups on the molecule are incompatible, and so we needed a better solution to this problem. Now, remember our initial goal. We want to take the alcohol and go straight to the CF3, so here's an early experiment. This is like when I was in lab and running reactions myself. So this is my experiment, like one of the few experiments that I actually ran in this slide deck. You can take some of these activated alcohols, in this case you can see the series here, and subject them to either the metal halide salt or the ester and promote the decarboxylation. And the yields on the bottom are not particularly ideal, but they do demonstrate catalytic turnover. And proof of concept in like year 2 of your career, that's a pretty good result. So we have 10% copper iodide, 30 to 40% yield. This combined 40% yield in one reaction that is still promising, and we can further develop that chemistry. So to develop this chemistry, we're ultimately going to try to make a new reagent. I'll tell you a little bit about the design of that reagent. The working hypothesis at this point is that the alcohol would undergo a transesterification or a condensation reaction, depending on which precursor you used here, to generate the halodifluoroacetate ester in situ. And then the copper-based catalyst system would promote the decarboxylated trifluoromethylation. Now, the problem with this proposed sequence is that the initial transesterification or condensation would generate a stoichiometric quantity of water, methanol, or some hydroxide, and maybe that was problematic. So you can run a quick experiment to test that. Take your substrate, throw in any of those potential stoichiometric byproducts and see if they antagonize the reaction. So on this day with no additive, the parent reaction gives an 80% yield. You can see in the presence of one equivalent of methanol or ethanol, you see that yield drop off. So we know this is a challenge, this is a problem, and now we need to solve that problem. We need to figure out how to generate a reagent for which the stoichiometric byproduct does not antagonize the reaction. So you can go about this problem several ways. You could have a grad student just go start making everything they can possibly think of, prepare it, try it, prepare it, try it, prepare it, try it, hopefully you get the right answer. We chose a different approach. In this case, we chose to get a bunch of these leaving groups and run the same reaction. Take our substrate, run the reaction with a bunch of these and see what does not antagonize the reaction. Then we can prepare a smaller subset of proposed new reagents. So that's the experiment I'm showing you here. The conditions, you can see similar conditions to what you've seen the entire time. Is the allylic substrate. We'll look at a variety of leaving groups, potential leaving groups, and see if they interfere with the process. In this case, your yield was 75%, not 85% for the day we ran this reaction. A variety of alcohols were explored. You can see trifluoroethanol was all right. It did not antagonize as much as others. A variety of phenols were explored, and perhaps some of those might be useful as leaving groups in this process. Thiols, you can see other nitrogen-based heterocycles. There's precedent literature for many of these serving as substrates for transesterification reactions. And so there was sufficient evidence in the literature maybe these might work. Ultimately, some of the ones that we probed and explored are highlighted in red, and then we need to go back and synthesize the comparable reagents and test them in reactions. So there were issues with a couple of them in terms of stability, hydrolytic stability, stability on silica, and ultimately we came to this phenyl bromodifluoroacetate ester as being the key reagent. So this reagent promotes the transesterification reaction. That transesterification reaction under our reaction conditions is promoted by the KF that's in solution. So stoichiometric studies, just looking to see what forms the ester, KF actually does. It's not copper, it's not just thermal, it's not other additives. The KF actually promotes the transesterification, and then we have this substrate prepared to generate to serve as the substrate for the copper-based catalyst system. The reaction works for a variety of substructures. Again, we're going from alcohol to CF3. These are one-step reactions. These are not the four-step sequences that had been used previously and I mentioned earlier on. So the yields are good enough. You can do some of the allyl substructures, benzyl and heterobenzyl substructures. The reaction of Brachyl group still gives those allenes with the right catalyst system. Okay. So I don't want to go through too many examples or highlight much here. I want to keep moving on, talk more about the science and how it might impact some preparation of target molecules. So this is an example that comes out of the literature of a group trying to make an agricultural chemical. They take the heterobenzyl substrate, convert it over to the heterobenzyl CF3 in 4 steps and 30% yield. Again, that sequence involves oxidation, 1,2 addition to generate the trifluoroethyl alcohol, and then 2 steps to reduce off that alcohol, this time using stoichiometric tin. You also have to use stoichiometric manganese early on. Okay. Using the first reaction sequence I mentioned before, you can generate the ester, isolate it, purify it, and then subject it to the copper-based catalyst system and deliver the same product in half the number of steps and double the yield. Alternatively, you can take the reagent I just showed you, do it 1 step, almost double the yield. Okay? Certainly saving steps and more economical for principles of green chemistry. Okay? So that's how it might apply to some campaigns. This was not the final target molecule. There's further functionalization of the furan that was done by the other group to make other compounds. Okay. So that brings us up to 2019, and there's another, nope, this was these two papers in 2019, and then what happens in the world? COVID, right? And everything shuts down. People can't go to college, can't go to work, can't go to the lab to run experiments, and so what do? We sit and we start reading, we start problem solving and doing what we can do on paper, and that's where the next project emerged. This next project emerged because we couldn't do anything for it, and we had to go back and think about new challenges and new problems and new solutions. So sometimes taking the time to stop and think and just, it's good. Okay, dig back into some literature, look back at your old notebooks, and that's exactly what happened. I'll give you a little bit more information on this. So this story actually goes back to a GRC conference in the US, 2018 notebook, and I had this written down. I really did have 3 question marks over this transformation. I was just sitting in the audience watching somebody else give a talk, and I was like, I got curious about how do you do this? There isn't a solution to this. We had a little bit of experience with this type of transformation. It's a 3-step process to do it in principle. This was that FDA-approved therapeutic I mentioned at some point during the course. That's an antitussive. The synthesis, the preparation requires taking the compound has the methyl and the methoxy group and protecting the nitrogen as this carbamate, demethylating over here, and then it's a 3-step sequence to convert the phenol to the boron using the triplet anhydride and pyridine, and then a meioborylation, and then you use the Hartwig trifluoromethylator reagent. That's a stoichiometric reagent for doing aromatic substitution reactions, and we got the CF3 there. Okay, 3 steps, 30% yield, not ideal, but good enough for medicinal purposes. Okay, so we need to improve that process, and again, COVID allowed us to do that. Now, to be competitive in this field, you have to have an awareness of other ways of preparing these aryl trifluoromethanes. And so I've summarized some of the most impactful methods here on this slide. The first 2 require harsh reagents, oxidizing reagents and or gaseous reagents that preclude the presence of sensitive functional groups and are difficult to run because like HF and SF4, like you don't want to be using those in simple academic labs. If you're going to make an impact with those, you're going to be in an industrial setting, specialized reactors, they decompose a lot of stainless steel and other things. Like you need specialty precautions and especially systems to be able to do these types of transformations. Radical functionalization typically occurs with poor regioselectivity, so we want to do one CH bond and not the others. That's a challenge. And finally, the metal-catalyzed cross-coupling reactions, number 1, are not the most effective right now. And number 2, if you have highly substituted derivatives, the preparation of the substrate itself might be tricky. So these methods generally fail when you have highly substituted target molecules. So if you have molecules for which you have many different CH bonds in the molecule, it's difficult to see why you would functionalize one position as opposed to the others. In some cases, preparation of the halide or carboxylic acid precursor might be a challenge in its own right. And with some of these other reagents, you can't have certain sensitive functional groups. If you have maybe 2 methyl groups next to each other, how are you going to selectively functionalize one and not the other? Okay, so a lot of challenges here if you had molecules of more and more and more complexity. Even though these are flat planar rings, they're still tricky to make currently. So there were several different mechanisms, and this is probably over the course of a month where we're going back to the books and the drawing board and planning different sequences. And here's one sequence that stood out. And so if you consider a reduction of a phenol with a metal-based catalyst system, that would generate an enone. In a subsequent step, use of the Rupert-Prakash reagent would generate the trifluoroethyl alcohol, and then we need to do an elimination and oxidation to get back up to the arene. So that was the working sequence. There are some catalyst systems to do this. There's really no minimal precedent for doing this, and definitely not with a CF3 group on it. And I'll mention later on why that CF3 group is pretty substantial and important. the next day, a couple days later, there was a realization that there's actually a really powerful transformation embedded within this figure. If you only focus on this second part, that would be really useful, because the enones themselves are very versatile substrates. You can functionalize those with all kinds of reactions. You have the alpha position, either one of them, beta position, you can do gamma functionalization. Maybe we can dial in substituents in a controlled fashion, really control their installation in terms of the regiochemistry, and with a wide variety of decades and decades and decades worth of transformations of these enones. Maybe we could be pretty creative and access compounds of more and more complexity if we can figure out how to promote the deoxyfluoroalkylation aromatization sequence. So this is where the innovation really is, connecting these two groups. Now, the work was done predominantly by Pankaj, a former student. He's doing a postdoc right now. Other individuals helped quite a bit over this project and are following up on some of Pankaj's additional leads that he left behind. But he did most of the work that you're going to see on the rest of the next three papers. So the solution, this slide is probably a year and a half of graduate work on one slide, and that's sometimes the way it goes. Okay. He developed three different solutions at the outset to this problem, and you'll understand in just a minute why we have three solutions for an initial attempt. The first solution involved the use of the Rupert-Prakash reagent to do a 1,2 addition reaction that generates a mixture of alcohol and silyl ethers, and you have both cis and trans isomers when you consider the oxygen to base group relative to that phenyl group. We did characterize all those and figure out what was going on there. You don't need to separate them. In the exact same pot with no purification, no workup, no anything, you can toss in PTSA, DDQ, heat the reaction mixture, and you get aromatization. Now, DDQ has two different mechanisms by which it can operate. It can operate by a mechanism that does hydride abstraction. If you abstract hydride from your substrate, you would get some type of a cation intermediate. It can also do H-atom abstraction. If you abstract an H-atom, you would get a neutral radical intermediate. Now, it turns out the initial substrate we were using was distinctly chosen because it's going to be easier to oxidize. It has a benzylic position that can stabilize these types of intermediates. So when you're starting a new reaction for methodology, pick something that's easy, that's going to be likely to give you success, and then move to harder problems. And that's what we did here. If the substrate does not have a stabilizing group, in this case the T-butyl substrate, the 1,2 addition reaction works just fine, but the oxidation reaction no longer works. 0% yield, that's also 0% conversion. We can re-isolate the material shown here. We do a little bit aqueous workup so we get all of the alcohol. You can re-isolate that. Okay? And again, that substrate does not benefit from an activated benzylic position. It's tertiary, it's pretty good for some mechanisms, but it doesn't work in this case. To demonstrate that the CF3 is really disfavoring the reaction, I like to show this example from C.J. Lee's group at McGill University. In their reaction, the 1,2 addition reaction of a Grignard reagent makes a comparable intermediate. The elimination and subsequent oxidation with DDQ occur under mild conditions. The CF3 is resisting oxidation. This occurs easily at 50 degrees Celsius. This reaction, I'll show you, goes through a similar vinyl intermediate, but we require 150 degrees to do this because of that CF3. So, how are we going to solve this problem? Well, there were quite a few different attempts at solving this problem and promoting the reaction. Ultimately, Pankaj found that you can do the 1,2 addition reaction, force elimination with SOCl2 pyridine, and then run the material through a silica filter that generates a semi-pure form of the vinyl trifluoromethane, and then we can use a combination of AIBN and NBS to promote the oxidation through radical intermediates. So there are no cationic intermediates in this sequence here. That works for both the unactivated and activated substrates reasonably well. If you have the activated substrate, you can go ahead and take the vinyl intermediate also subjected to PTSA DDQ and promote the oxidation. So you have 3 different sets of conditions. If you have different substrates, you get a different attempt. And we know that for any individual reaction we try to run, many times you need multiple sets of conditions. How many amide bond forming reactions do we have? How many different reactions to go from alcohol to an aldehyde do we have, right? Plenty of different sets of reactions. For any individual transformation, it's okay to have multiple solutions that you can turn to for different substrates. So the reaction works for a variety of substructures, some of which are shown here. Nitro and cyano groups, electron deficient. You can use halides that can be further functionalized by a wide variety of cross-coupling reactions. Donating groups are tolerated, amines, ethers. You can see aliphatic systems. If you have groups, I'm talking about these. If you have groups that have acid-sensitive substructures on them, you can get them to work. You just have to remove the acid and lower the temperature. I'll show you a little bit more data on that in just one slide. And orthosubstitution is tolerated. Many times orthosubstitution will be difficult with transition metal-based coupling reactions, and we can do it here reasonably well enough. In addition, I like this example because if you had radical functionalization chemistry, and if you had a CH here, you'd never functionalize that position with a radical. It's too sterically hindered for the radical to attack there. If you try to use like the Schwartz method, where you have a methyl group and you trichlorinate it and dechlorofluorinate it, there's no way you're going to hit this methyl group as opposed to the other 2 selectively. So there'd be some challenges there. So here's an example of a vinyl ether here. Vinyl ethers hydrolyze under acidic conditions. That's been known since the 40s or 50s. That's an old reaction. In this case, the conditions, the oxidation conditions that use PTSA DDQ give you a mixture of the phenol and the ethers. If you remove the PTSA and heat the reaction a little bit less, you can improve the yield and improve selectivity for formation of the ether product. Similar story is true for products bearing an ester. TMSCF3 is strongly nucleophilic and will react with most esters. So to disfavor the reaction of TMSCF3 with the ester, you need to use a bulky ester, and that's why I have the T-butyl group on there. The problem is that the T-butyl group comes off with acid. So there's a chemical incompatibility there. If you do the oxidation under the initial conditions, you form the carboxylic acid. Great yield if you want to make a carboxylic acid, but if you want the ester retained, that's not the way to do it. So if you remove the PTSA, use a less forcing temperature, you can invert the selectivity, generate the ester. We do have a next generation set of conditions that improves that yield and selectivity even further. Okay, so we're still working with that. So the strategy itself enables access to a wide variety. So a wide variety of products. In this case, I'm highlighting that you can take commercially available simple materials and in a single step access comparable trifluoromethanes. And if you try to use other methods, the precursors don't work. You need a de novo synthesis, like that. You have to figure out a new synthesis of it. In some cases, they're pretty expensive. This is a reasonably expensive chemical when you look at that price, but there are chemicals of comparable complexity that you can convert over to the trifluoromethanes. So again, we just want to think about other starting points that are orthogonal to things that might be unavailable or ridiculously expensive. Using routine synthetic organic logic that you have been introduced to since your sophomore organic year of chemistry, you can access all kinds of substructures. So I'm just going to show a series of short syntheses that can convert a simple starting material into a variety of products. We can use a simple bromination reaction, generate a vinyl bromide and convert that over in a short synthetic sequence. That bromide enables functionalization by a wide variety of cross-coupling reactions, one of which we can show there. There's the Ho-Suzuki reaction. That product might also be accessed by doing the Suzuki reaction first and then the deoxy functionalization trifluoromethylation reaction. That gets you the same product. If you want a functional handle here at this position to do further chemistry, you can introduce the halide in that step. here NCS to introduce the halide. Then we convert that over to the final product in reasonable enough yield. If instead we want to invert the halogen and carbon-based substituents, we can do that, but we need a new synthesis. In this case, we can go back. There's an activated methylene here at this position, and we can do a functionalization there with our carbon-based reagent first. Then we do the halogenation. We've inverted the carbon and halogen-based substituents there, and then we can convert that substrate, that enone, over to the aryl trifluoromethane in the next step. Lots of opportunities. Sorry, I'm talking so much. It's fine. You can't do notes after all this much. Okay. So there are many opportunities to use routine synthetic organic logic to build substrates and convert them over. Okay, so that's what I've tried to highlight initially. You can also generate these enones by a wide variety of other strategies. There's reductive conditions for getting into the substructure. You can do other annulation reactions to introduce the enone substructure with high complexity. I'll just show a couple of examples real quick. Here we have a metal-based coupling reaction that couples two simple building blocks to make a tri-substituted enone, which ultimately gets converted into a tetrasubstituted arene. Other annulation reactions can also be used. In this case, it's a net 5+1 cycloaddition reaction to snap in this C1 unit bearing a quinoline moiety. This ultimately converts over in reasonable yield. Palladium-based catalyst systems and some other transition metals don't like purity like nitrogen atoms, and so many times this type of substructure might be problematic for some other systems. Natural products might also have enones and ketones, cyclohexanones, built in them, and so those can serve as substrates themselves for further functionalization prior to aromatization. So here we do a 1,4 addition reaction, introduce a new substrate, and then convert it over with the initial set of conditions. And so there's no shortage of creative things you could do to take enones, prepare enones, highly substituted enones, and convert them over. Okay? So that's the moral of the story here. At this point, we focused on the CF3 group. There are many other useful fluorinated functional groups that one might want to introduce into your molecules, and the method can also be applied for other fluorinated functional groups. So here's a slide in which we will look at the 1,2 addition reactions of different fluorinated functional groups, and we use one of the sets of conditions before two different sets of conditions here to promote the aromatization. A variety of fluorocarbons are readily added in. In some cases, we use a silyl protecting group and a metal fluoride to generate the effective anion. In other cases, the higher molecular weight fluorocarbons, you can get away with the iodide precursor and use a lithium halogen exchange to generate the nucleophile. Those oxidize in the presence of PTSA DDQ. If you have other heteroatoms in your nucleophile, such as oxygen, so this would be a ketone, this would be an ester, this would be a sulfone, those fluorophosphonates, like that was the very last slide before we broke for lunch. Okay, you can do 1,2 addition reactions with those. You just need different strategies for generating the nucleophile. They do the 1,2 addition reaction just fine. And then the aromatization requires the SOCl2 purity conditions. Okay, so you can do all kinds of things with that. Heterocycles are tolerated, very important for pharmaceutically active agents. Electron-rich heterocycles, carbazoles, indoles, thiophene are tolerated. Imidazoles, electron-rich, electron-deficient pyridine-like systems are tolerated. This slide demonstrates that you can have the heterocycle tethered to the ring that is formed, or it can be benzannulated. Okay. What about rings in which your heterocycle is attached, or part of the CF3 is attached to the heterocycle that you form, right? I haven't shown that yet. So the proposed sequence is here. The proposed sequence would require a substrate that looks something like this. You do a 1,2 addition reaction with TMS-CF3, eliminate, and then we need to do an oxidation here. The challenge is there's an incompatibility with TMS-CF3. TMS-CF3 reversibly forms difluorocarbene, and the difluorocarbene will react with NH bonds. It makes the NCF2H. So we need a protecting group. But if we choose strategically a protecting group, perhaps it might undergo an elimination reaction and generate one of the unsaturations, and then we're just one unsaturation away from the final product. Okay? And this should be an easy step because that's the step that forms the aromatic ring. So that should proceed presumably under more mild conditions. So hopefully you're thinking a little bit about like what group I would put on there. Ultimately we went with a sulfone. If you have an SO2 pH, this is a sulfonamide group. That sulfonamide group might leave with either strong bases that could deprotonate and promote the elimination, loss of SO2 minus. Alternatively, under radical conditions, you can do H-atom abstraction and then a radical elimination of phenyl SO2 dot. Okay, so you have multiple different opportunities for success with that protecting group, and that's why we chose it. We can try a whole bunch of different conditions to promote the elimination. Ultimately, what works, you do the 1,2 addition reaction, as you've seen many times, elimination to generate the vinyl CF3. We do have a quick silica filter here to clean out some of the junk, and then just simple DDQ does it. Temperature a little bit more mild than some of the other systems. Okay. So I'm going to pause there on just methodology. There are many, many, many different opportunities to use this strategy. I mean, it's not just a reaction. I think it's a strategy. And then you can make all kinds of different molecules with that. A theme from the course involved thinking about reactive intermediates and how fluorination perturbs the reactivity of molecules. Previously, we were thinking about reactions that occur in biological settings, but let's pivot now and just talk about the organic chemistry and how the fluorine perturbs the reactivity of the oxidation sequence. Okay? So this is similar to one of the slides I gave in problem set, and we talked through it once for those of you who are in the class, but maybe it'll make more sense now that you've seen the preamble, the rest of the papers before it. The key data shown here summarizes the different temperatures that are required for oxidation of these different substrates. So we have the example from C.J. Lee, that's a styrene, the trifluoromethyl vinyl substructure that has a stabilizing group and the one that has a non-stabilizing group. Low temp, good yield. High temp, good yield. That thing doesn't like to, it laughs at you when you say, I'm going to oxidize you with DDQ. Okay, doesn't do anything. So to estimate how these reactions are proceeding, Pankaj ran a series of calculations, initially doing hydride ion abstraction, calculating hydride ion affinities. And so these are calculations in which we systematically remove H minus from the various positions and calculate the energy associated with H minus and the carbocation. Okay. And we focus on 3 different positions, the 2 allylic positions and then the position here that's attached to the group shown in blue there. For the model systems, we have 6 systems here that we'll look at initially for this slide. You have a styrene with the stabilizing group, a styrene without a stabilizing group. You have just a simple methyl group. We didn't study this experimentally, but it's an important benchmark to compare to the CF3 group. Okay, so it demonstrates, how difficult is it to oxidize this type of a substructure to make a toluene relative to a trifluorotoluene. So that's a control substrate. Just to calibrate everybody, with the easiest example you have here, the hydride ion affinities are reasonably low in all cases. You can see the weakest CH bond here. If you make cation there, it's allylic, but when you put the cation here, you also have benzylic stabilization, so you have a nice extended conjugated system. The next substructure over also has a reasonably, it forms a reasonably stable cation over here, and that stable cation also would extend and resonate all the way through the system there. I hope it's not dying in battery. You see it jittering a little bit more, and that's not me, it's jittering on its own. So we'll try resetting it. Note there are other weak CH bonds in the molecule, but we don't need more. Like any of these are good enough options. We'll go over and look at the next pair. The next pair has the methyl group here. The allylic position is still reasonably weak. as is the benzylic position. So there are multiple opportunities to abstract H minus, generate a stable carbocation, and then continue the sequence. And the same thing is true for the next example down. You still have a weak allylic CH bond here. This one's tertiary, this one's still allylic, but there are still a couple of reasonable options there to initiate the sequence. In contrast, when you get to the CF3, you get significant perturbations to both allylic positions. So look at those hydride ion affinities. You're upwards at near 250 kcal per mole and 245 down here on the lower case. Those are too much, like they're too hard to rip off those hydrides at those positions. Now the difference between the substrates is right here. It's the benzylic position relative to just the regular tertiary position. This is still weak enough that you can oxidize it under high temperature, but this one's just too high and it resists the hydride abstraction at that position. That's how we walk through and rationalize the oxidation data that we see here on top. Okay, so summarize that there. Low HIAs, low temperature, higher HIAs, and then this one doesn't do anything at all. Okay. What's going on? Okay, there we go. So there are other mechanisms by which one can oxidize a substrate, and perhaps you could do one electron oxidation. There are some oxidation reactions that we're aware of in the literature that involve some type of strong oxidant ripping an electron out of the substrate. I'll just show you a series of model substrates and then this one up here, and these are calculated one electron oxidation potentials. You can see for the styrenal system, 1.4 volts. We have a methyl group here, a little bit higher in energy, 1.6 volts. You put the CF3 group on there, and you're upwards of 2.5 volts, so certainly resisting oxidation if we think about any mechanism that involves single electron oxidation of any of the moieties on the molecule. So that's not going to work. Pankaj did make some attempts in this space, but ultimately we found an alternate strategy that involves H-atom abstraction. So by H-atom abstraction, you're going to go through the neutral intermediates. Okay. So we might look at the substrate and identify the weak CH bonds. You have C3, C6, and then C4. Abstraction of any of those hydrogens would give you radicals. Just for purposes of the discussion, we're again going to just look at a smaller subset of molecules, not all the phenyl substituted ones, just the T-butyl substituted ones that were previously resistant. The bond dissociation energies at C3 are reasonably low regardless of the substitution. Phenyl, H, CF3, all of them have weak enough bond dissociation energies to rip off with an appropriate reagent. Okay. At the other position, the C6 position, you also have reasonably weak CH bonds there. So you have opportunities to initiate oxidations that involve an initial HAT step using this type of strategy. Ultimately, what works, remember, NBS, AIBN is going to be the series of reagents that we use to promote this. Again, we think it's going through these types of radical intermediates. Okay. And we do have some experimental evidence. Takeaway messages. If you're trying to go through cationic intermediates and you have your CF3 in the molecule, that's tough. Okay, you're facing an uphill challenge. If you're exploiting a moiety that can stabilize the cationic intermediate, you have a chance. But instead, if you turn to neutral intermediates, you have an even better chance of getting these oxidations to occur. So the CF3 group is really powerfully changing the mechanisms that we have to use to promote this oxidation. Okay? So, ongoing, what are we doing in this space? We are developing next generation systems for this transformation. We have things already. They're working down below 50 degrees based on some of the learnings and application of other cool, innovative chemistry behind the scenes. So look out at that for the future. And we're also always thinking about other fluorinated functional groups that we can use. So that kind of concludes where I wanted to be at the end of the first part. And I think we started like at 2:15 or so. So I'm like 55 minutes, pretty close to where we wanted to be. How long of a break do we want to take before we move on to the next sequence?
5 minutes. It can be quick.
5 minutes?
Short break.
Yeah. Okay. We'll take 5 minutes and be back.